Group 11, and our project is predicting Uber and Lyft ride demand using neural networks. So our motivation behind this is that urban ride demand varies significantly by time and location. As a result, ride-sharing services like Uber need to flexibly respond to these fluctuations. However, current systems often fail to predict this demand accurately, leading to vehicle shortages, over-dispatching, and sudden demand spikes. Our project aims to address that challenge by developing a neural network-based forecasting model to accurately capture hourly ride demand patterns per zones within a city. So the data set that we're working with is an Uber and Lyft data set found on Kaggle, and it is for the city of Boston in Massachusetts. We had some input data features such as date, time, pickup location, destination, distance, and even more. And we pretty much shortened that down to three main things through preprocessing. Date time, which is the timestamp of the ride rounded to the hour. Rides is the number of rides in that given hour. And source is the pickup location. Note, we did have to fill in some missing time intervals with 0 to create a continuous time series suitable for forecasting, and we omitted things such as price, weather, and other external regressors, focusing solely on temporal patterns. And this shows our data set, how we shortened it down by getting rid of some of the columns and data we did not need. And we can see our average hourly ride demand patterns in a specific zone called West End in the city of Boston. Our forecasting prediction is shown on the bottom right, which you can see accurately captures that demand pattern for multiple days. Now, our model architecture that we're using is neural profit. And neural profit is basically an autoregressive MLP-based model. And what that means is that it uses prior predictions as inputs to make future predictions. And that's pretty much what our forecasting is doing, is using prior weeks and days of ride demands to predict the ride demand for the following weekend, for example. And we did this by training the neural profit model on different zones within the city to pretty much give each zone a distinct ride demand pattern and capture those local variations more effectively. And we did this by forecasting for 7 days in advance after our data set ends. And our performance metric we used was an MAE. We compared this to a naive or dummy model to see how our model performed. And here you can see our forecast, which is the blue squiggly line. As you can see, it initially struggles to capture those initial ride demand, but as there's more data that it works off of, it more accurately captures the actual ride demand throughout the following weeks. And at the end, you can see the forecast for the week of December 18th to the 25th, in which it shows its prediction for what it believes the ride demand will be. Now, our performance evaluation we compared to naive prediction, which pretty much means it took the actual ride demand of the previous day and said it would happen for the following day. Note, we can see that's the orange line, and the forecasting model is still the blue line, and the actual is the black line. Now, we use the MAE, which pretty much is saying per hour how wrong is our model versus the actual. And we got an improvement of 33% because the naive MAE was 52.27 and our neural profit model was 35. Note, our model showed consistent improvement in MAE across all zones, but in this case, you're only seeing West End. In conclusion, we were able to develop a zone-level demand forecasting model using neural profit, and we're able to pretty much independently capture local ride demand patterns and forecast that for following weeks. And compared to a naive baseline model, our approach consistently reduced the MAE across all zones, and it supports smarter, demand-aware vehicle allocation in urban mobility systems. Thank you.